Okay, this section is normal curve. And maybe you've seen this before. This is called the bell curve, the normal curve. Okay, most people are average. That's why it's the highest. And then as you get farther away from average, the percent decreases, which makes sense. If I gave a test and the average was 80, if you got maybe 100%, you'd be here. If you got a 20%, maybe you'd be down here, right? It's the bell curve. It's used a lot in any state standard testing, ACT, SAT, baby weights, right? Heights. How do you know if your baby's healthy? It's in the normal distribution. Okay, so these are the percents we use. If you were to Google normal curve, you're going to get 100 different percentages. They're all approximately the same. Some of them round more, like they'd use 34.02. But with the author, we're going to agree to use these percents, just so you know if you have a different textbook, it might be different percents, not by a lot, but by a little bit. It is also over there on my classroom wall, and that will always be up there. I don't take it down. You can use that. Okay, so you don't have to have this memorized, is what I'm saying. You can use it. Okay, so a couple of things. If this is my mean and we count one standard deviation both ways, we kind of did this the last section, 68% of my data is within one standard deviation. Okay, if I go out two standard deviations, 95% of my data is within two standard deviations of my mean, so go both ways. And then within three standard deviations would be 99.7%. Okay, so they use this to determine a lot, like scholarships. You have to have above a 26 on the ACT. Why? Because you're going to be in the top 90% of students. That's why they set certain ACT scores is what they are, because with the bell curve, you're proving your way up here. You're better than 90% of the students. Okay. Okay. Using our bell curve there. Can I get anything on there? Okay. So the first thing we're going to do, I can't fit it all on there, so we'll do this, is I like to set up the normal distribution. Okay. So it tells me the reaction times for hand-eye coordination tests administered to 1,800 teenagers are normally distributed with a mean of 0.35 and a standard deviation of 0.05. Okay, so let's set up the bell curve. So in the middle here is going to be 0.35. And then I'm going to count 3 standard deviations to the right and 3 standard deviations to the left. Okay, so I'd go 1, 2, 3, 1, 2, 3, and I'm count by 0.05s. So this would be 0.4, 0.45, 0.5. This is going to be 0.3, 0.25, 0.2. So here's my mean, 0.35, here's my standard deviation. So if I set up a bell curve, right, my mean always goes in the middle, 0.35. And just like I did last section, you count by standard deviations. Three times. Add 3 times, subtract 3 times. So since my standard deviation is 0.05, what's 0.35 plus 0.05? 0.4 plus 0.05. 0.45 plus 0.05. 0.5. And then you subtract 3 times. So 0.35 minus 0.05, 0.3, minus 0.05, minus 0.05, 0.2. Okay? And then I can fill in these percents. This is 34, 34. This is 13.5, 13.5. You should know it's symmetrical. 2.35, 0.15. Okay, once you have this all set up, you can then answer questions. Okay, so it says, about how many teens had reaction times between 0.25 and 0.45? So I look 0.25 to 0.45. I'm going to add up those 4%, okay, which is what? 95%. But I don't want percent, I want how many teens. So I'm going to take 95% times the 1,800. So 0.95 times 1,800 is what? 1,710 teens. What is the probability that a teenager selected at random had a reaction time greater than 0.4 seconds? So 0.4 seconds, and here's 0.4 seconds, and I want greater than, I'm going to add up those 3%. Take 13.5 plus 2.35 plus 0.15, and I get 16%. And I can leave it as a percent because this one says what's the probability. Try another example. So Ms. Chapman gave a test in her algebra class. The scores were normally distributed with a mean of 85 and a standard deviation of 3. So again, we're going to set up the normal curve here. The middle value is always the mean, 85, and we're going to count by standard deviations. So 85 plus 3, 88, 88 plus 3, and 91 plus 3. And then I go left, I'm going to subtract 3 standard deviations. So 85 minus 3, 82 minus 3, and then 79 minus 3 is 76. Good. Okay, then I can throw in my percents, 34, 34, 13.5, 2.35, 0.15. Okay, now I'm ready to answer some questions. What percent would you expect to score between 82 and 88? So between 82, 88, I add 34 plus 34, which is 68%. And it says what percent, so I'm good there. What percent would you expect to score between 88 and 91? So 88 and 91 is just right here. So 13.5%. What is the probability that a student chosen at random scored between a 79 and a 91? So 79 to 91 would be 95%. Yep. What percent or what probability is going to have the same type of answer? Examples on tires. Anyone that owns a car should know that you need new tires every 30,000 miles. Otherwise, they'll be too bald, right? Tires usually last around 30,000 miles. Okay, so we're going to set up this normal curve first. 30,000 is my average, so that goes in the middle. My standard deviation is 5,000 miles. So I'm going to count by fives. So 35, 40, 45, subtract 25, 20, 15. Okay, I can throw in my percents. Get my normal curve set up. About how many tires will last between 25 and 35. So notice it says how many, not what percent or what probability. So 25 to 35 is what? 68%. So I take 0.68 times, there's 10,000 tires made. So how many tires would that be? 6,800 tires. About how many tires will last more than 40,000 miles? So more than 40,000 miles would be here, 2.5%. Add those two together. So 2.5% as a decimal times 10,000 would be what? 250 tires. Okay. About how many tires will last less than 25,000 miles? So less than 25,000 miles would be here, and I'd had to add up these three. So 16%, add up those three numbers, so 0.16 times 10,000 is what? 1,600 tires. What is the probability that if you buy a radial tire at random, it'll last between 20,000 and 35,000 miles? So between 20 and 35, I add up those 3%. So 81.5%, right? Because it says what's the probability.